All right, so let's talk a little bit about mechanical testing. And when we're talking about like physical properties or mechanical testing, there's a lot of different variables we can throw at it. So we can be looking at how do the physical properties change with temperature? How do they change with time? How do they change with different atmospheres and environments? So this is not going to be a cohesive, like fully encompassing, conversation on materials, physical properties. That's just huge.
Yeah.
What we are going to talk about is something that is commonly referred to as UTM. Well, I guess that's the name of the instrument that would do it. We call it a universal testing machine, which I think sounds a little bit full of ourselves here. This is not a universal testing machine. What we are looking at here is specifically physical properties. So we're going to use words like modulus, elasticity, potentially like hardness. We're going to be looking at like brakes, or creep. That looks like I wrote reap. So what we're looking at is how does our material react to physical inputs rather than chemical inputs or electrical inputs or whatever else. The instrument, the universal testing machine that we use is an Instron, is manufactured by the company Instron. They're one of the biggest names in this sort of like mechanical testing business. They have a lot of customizability, and so no two Instron instruments really look all that similar to each other. They are all going to have different properties and different capabilities depending on what you're doing. Instron focuses more on industrial applications. So they work really well if you're in a factory making, ceramic crucibles, and you're only ever going to be making ceramic crucibles, and you're going to test hundreds of exactly identical ceramic crucibles every month. That's where they're the strongest. I apologize. That's where they're the strongest. They have the ability to kind of change what methods they're using. So you randomly bring in, instead of a ceramic crucible, you bring in like a ceramic disc. Okay. And you're like, okay, I want to run this. It'll be similar, but a little bit different. They do have some customizability. But because Instron mainly focuses and is mainly really adept at handling specific industrial applications, makes it a little bit complicated for us in a research setting, where every single sample that walks through the door has a different maximum, has a different minimum, has different sensitivities, needs to be clamped or held in place differently. Just makes it a little bit complicated for us. Their software is more than capable of handling stuff like that. But you have to kind of know a lot to do a lot on an instrument that is highly capable of a little bit of everything. Yeah. So the software of the Instron is I think the hardest thing to learn, because the mechanical properties are things that we have been playing with since we were old enough to hold two toys in our hands. So like around the age of 6 months, we start playing with mechanical properties. We're like, okay, if I throw this, does it bounce? Does it just hit the floor? Does it break? If I pull these two things apart, how do they react? What can I break? What can I not break? So mechanical properties, we're all pretty like familiar with it already. Let's talk first about modes. And when I say modes, we're talking about like different ways that we can. So modes of test. So this is, how can I hold or manipulate a sample in order to get information about the sample? Have you done any mechanical testing?
Little.
Okay.
I don't remember all of what we did, but...
That's totally fine. Do you remember what the sample was like or how the sample was being held in the tester?
Not exactly.
Okay. So when you are holding, let's say you're holding, I don't know, any number of things. You're holding a piece of paper. What is one way that you can move, one direction you can move your hands and to see how the paper reacts? You're holding the paper out in front of you.
Pull it.
Pull, yep. So I can take a thing and I can pull in either direction, and my hands here are gonna be lined up, so I'm in line with each other. Do you know what we call that in mechanical testing?
No, I can't think right now.
That is tension or tensile testing. If we go opposite of that, again with our forces lined up, now I am pushing down on the thing. That's compression. Do you have siblings?
Yeah.
Have you ever done a rug burn on someone's arm?
Yes.
Do you, so in that case, we are taking a sample, in this case, you know, a sibling's arm maybe, and we are twisting the top in one direction and the bottom in another, or we could do side to side. All of these I could turn around, like rotate around in a circle, and that would be just like equivalent essentially. And the name for this one is torsion. And then we also, actually I'm gonna move those words down. We also can apply any sort of force off center of each other. And that could be both of them, like in sort of a compression mode, like I've drawn first, or that can be in a sort of tension mode. That is called shear. Scooch all those over so we're not quite at the edge there.
Perfect.
Good. Couple more modes. If I've got sort of a long, flat sample, have you heard of 3-point and 4-point bend testing?
I don't think so.
Okay. In 3-point and 4-point bend testing, we are measuring flexure. And it's just how does the material flex, bend, basically. This one is called a 3-point. And we've got two bottom supports that I've drawn with these circles, here and here. And those circles, just those supports stay still. And then I'm just pushing down on the center of the sample. And it's going to flex in that sort of like, I'm doing
Right.
handwriting, so there are limitations to what I can do. But we're gonna get this sort of like bending to it. 3-point bending creates sort of this triangle area of effect. So the force is being felt along this area here. There is another option. Oops. With the same 2 bottom supports, but this time we use 2 top supports that are centered between the 2 bottom supports. We call this 4-point. I know that's, really surprising. If I call the first one 3-point, the next one 4-point. Instead of the triangle shape, 4-point bend testing has this sort of trapezoidal area of effect. And you can see relative to the size of the sample, 4-point bend testing is affecting more of the sample. So 4-point is considered to be a better choice in most circumstances than 3-point because you're looking at more of the material.
Gotcha.
But sometimes your sample is too small and you just can't do 4-point. There are just limitations sometimes. And the last one is called cantilever. Cantilever testing can look like 3-point or 4-point bend testing. It can also look like half of a 3-point bend test. But if you think about this is similar to like a diving board. Let's see. Cantilever can also be where you grip one side from the bottom and one side from the top. I'm kind of drawing these grips as tier shaped here. So these 2 are anchored to the bottom, and this one is anchored from the bottom. And then this middle one and this end one are anchored from the top. A little bit hard to see when I'm drawing it as simplistically as I am. But with cantilever, you have the ability to pull the sample upward or push it downward because we're clamping the sample instead of just with these ones, we're just pushing down on a point on the sample. But these 2, you actually like grab the sample and you can push up and pull down, or both. You can kind of do like an up, down on the sample.
Gotcha.
But all of these are types of flexure. All of these modes can be done with creep. Do you know what creep is compared to, say, like a static test?
No.
Do you know what creep is just generally? Or you just remember the word?
I just remember the word.
Stellar, amazing. So creep is running any of these tests extremely slowly or even with a static load or displacement. So this would be like, so creep is done slowly, sometimes with constant force or displacement. And we'll talk about exactly what is force and displacement in just a moment. But force is these arrows and displacement is how far the arrows travel in, this set of pictures. So with tension, that would mean that maybe I pull and stop. And then I hold it at this extended position for a day or 3 or maybe only for like an hour or two. And I measure, if I stop at this position, does the material relax? Does the force change? Or does it get stronger? Which there's probably material that does, but I can't think of one. It may also be in compression, I put a certain weight on top of the sample and I measure how long does it take to collapse. With like a memory foam, I put a single weight on it and it's going to collapse slowly over time. So in that case, I'm measuring the displacement as it changes over time. But creep is very much time dependent. It is not just how does pushing or pulling affect the material. It is how does pushing and pulling over time affect the material. That is also related to fatigue. Where we're looking at time dependency. Fatigue tends to be cycle dependency, where we are looking at, as we cycle the force on and off, how does that affect the material? Where creep is going to be just like cycle it on and leave it alone for a while. So for all of these tests, we are applying, and that's like no matter how you're holding the sample or gripping the sample, we are applying force, whose unit is newtons, and we are measuring displacement, which is millimeters. So if I push on this thing, how far does it go? There are some instruments that do vice versa as well. So I could also apply a displacement and measure the force. I don't know why I capitalized force. That was weird. So there's like two options here for like how we can measure and run these. But either way, force, displacement are our two kind of main things that we are measuring here. And let's assume our sample's really simplistic here just for a second, because that's going to make our lives a little easier. I'm gonna use my grid here to make myself a nice little sample. So I'm gonna draw this nice kind of rectangular sample. Ta-da. Yay to the grid for vaguely straight lines. And maybe I'll use the gray to fill in those like lines in the background. There we go. Three-dimensional shape. And we can measure our specimen here. I've got the width of the sample, which I'm going to call W. And that's like a left to right measurement. I've got the depth measurement, which I'm going to call D here. And then I've also got the length from the top, to the bottom length. So I've got these measurements. This is so very hard if you've got an irregularly shaped sample. For mechanical testing, you want everything to be very regularly shaped so that these values are very consistent.
Okay.
And from that kind of information there, if I shrink down my pen just a little bit, I can figure out the cross-sectional area. So I can draw this square here, and the area of that square is width times depth. So this is cross-sectional. So while we are running our test here, we're going back to 100%, I know these things about my specimen. Ideally, I know them for every single specimen that I'm going to run. And I can turn these force and displacement values into something called stress, which is done with a sort of sigma. And I can measure something called strain. Are you familiar with those?
Yeah, to an extent.
Okay. Do you have do you want to share any neurons connected to those words that you've got? You have not no stress?
Not much, no.
Great. Okay. So stress is related to the force. And how do I do that without messing this up too much? So force. Stress is a sort of measurement of force with respect to the sample. Force is just, it exists in a vacuum, as the metaphor goes.
Right.
I don't have to care about what I'm putting the force on. The force reading is the force reading. Stress is the force reading as it relates to the sample. So this is newtons per A, and I wrote A a second ago, so newtons, or let's see, sorry, I'm mixing things up here. It is force per area, which is newtons per millimeter squared. Because like we're usually working on the millimeter scale, it can also be newtons per meter squared, newton per centimeter squared. It's newtons per square area.
Okay.
And a newton per millimeter squared is the same as a megapascal. So MPa, that is the unit for stress. And I always put my units in brackets. I don't know why, that's just the rules. It's my rules. I don't know if there's anyone else who does that.
It looks good.
And that PA is Pascal, Pascal, a human being who, did some important scientific work.
Right.
Along the same vein, the strain is our displacement over the length. And we're talking about the original length here. Some people, instead of just writing an L, will call it L0, because the displacement is going to change as I, pull on this sample or push on this sample. The length is going to change. So we'll often write this as delta L over L0, delta L being the change in length. And the problem is this is millimeters over millimeters, and that means it's unitless. Often we will put this in a percentage. So it's just percent change. I didn't specify it, but so force can turn into stress when I apply it to a specimen, a singular item, and displacement can turn into strain when I apply it to a specific specimen.
Okay.
Questions on that?
Nope.
Okay, so this is the kind of graph that we're going to get, and you can graph it as force and displacement or as stress and strain. Yes. So my x-axis is going to be displacement or strain, which is that epsilon value. And I probably should have said out loud, but that is not just like how I draw E's. That's like a Greek letter, just like the sigma is a Greek letter as well. And we're gonna get some nice looking lines. And the line can kind of shoot straight up, and then the sample breaks. You can get sort of a slower, and then the material breaks. You can also get this sort of like funky, curvy situation here. We're going to change some of these colors here. There we go. Sorry, I hope I don't have any red-green people who need to know this information. Red, I should just change that to, none of my colors are gray right now because I just used blue. With different, so this is a stress strain graph, with different information we can, or with different types of material. There we go. Different types of materials are going to give us different graphs, different shapes on the graph. So we have a metal, a plastic, and a polymer here, and for now I'm going to write them. Oh, sorry, I said that backwards. A metal, a plastic, or polymer. I said plastic and polymers. If they were two different things, there are people out there who probably would tell me that they are separate categories, but for the function of this, they have very similar mechanical properties. So we've got three kind of overarching material types here. And let's think through what's going to happen to a material as we pull on it. So let's say I grab a ceramic, and assuming I'm superhuman and can actually, pull on a ceramic instead of my fingers just slipping off, is it going to have a lot of displacement in it? No. So ceramic is going to have low displacement, which instead of writing displacement, I'm going to write strain. It's not going to have a lot of strain. And is it going to have a lot of force or not a lot of force? Is my superhuman going to have to work really hard to break it?
Yes, lots of force.
Yep. So we would call that high stress. Which of these has low strain and high stress?
The steepest one.
The steepest, my red one. Because red and orange are empirically different colors. So we're moving bottom to top for some unknown reason. It's just the order we've chosen. I've chosen. I won't implicate you in this. So a polymer, is it, if you're thinking about like you've grabbed a piece of plastic or something and your superhuman is able to pull on it, is it going to have a lot of displacement or not a lot of displacement?
Probably a lot.
A lot, yep. High displacement. They tend to be very stretchy. That's why we use it in our clothing, right? Is because it provides some elasticity to our clothes. And then how strong is it gonna be? Are you gonna have to like try really hard to break this, or is a plastic gonna be like kind of weak?
Kind of weak.
Kind of weak, yep. Low stress. And which of ours, I see actually on your notes, you have already labeled them all, so A+ for skipping ahead there. That is going to be our purple line here. Wow, even the purple has very low contrast. I'm sorry to anyone who watches this ever. That's what the arrows are for.
Yes.
And then metal, I've already used high and low. So a metal related to a ceramic and a polymer, if we're creating this like spectrum, it's going to have some strain. Oops. Some strain, some stress. Now, this is not at all like empirical truth. There are some polymers that are stronger than some metals.
Right.
So this isn't just like the real world all the time.
Yeah.
But generally, metals, and you'll actually notice my ceramic, it's gonna go straight up and then break. There's really no point at which the metal or the ceramic is going to give or yield. Where the metal, if you've ever like bent a paperclip back and forth, you're doing, at that point you are doing a cantilever test on your paperclip. And you bend it back and forth, and there's one of the bends you can feel it give. And that's usually like 1 or 2 bends before it actually breaks. But you can feel like, ooh, there was that loosening of the material. So that's this point right here. It went straight up and then it kind of like loosened right in here, and then it broke a couple bends later.
Right.
That's the idea there. Plastics, they also have this sort of region where they will stretch before actually giving. But once they give, they tend to stretch and stretch and stretch for a while before they actually break. So this is kind of describing, you can see this like, these shapes can tell us quite a bit about what's happening in our material. So let's grab, I'm gonna draw another polymer because polymers tend to do some of the more complicated stuff, I guess. Maybe not complicated is the word, but as far as having lots of different events over the course of a mechanical test, a polymer tends to have a bunch of events, where a ceramic, like, that was pretty darn boring. We just pulled it and it snapped. So same units here. I've got stress and strain on my axes, and I'm gonna label a bunch of things here. I've got a straight line. I've got a point where it kind of gives, and that point where it gives I'm gonna put down here on the axis, and I've got a region here. I've got a region here. So just like before, I'm gonna like draw all this out, and then we're gonna talk about where all of these things come from. And also super fun is I've got the area under the curve, and I'm not really sure how I'm going to indicate that, but we're gonna try. like the back and forth. I just didn't exactly like the back and forth. There we go. An attempt to illustrate area under the curve. And we'll fill that area in there. I don't know. Okay. And just like before, I've got a bunch of properties. This time I have, oops, modulus. I've got plastic deformation. I have elastic deformation. I have break. I have I think that one we pulled. I'm gonna just put energy. That's like the total energy that went into the system.
Gotcha.
Okay. Do you recognize any of this language?
Forgot what modulus is.
Okay.
Plastic deformation is when it deforms, but it goes back. Or is that elastic?
Elastic.
That's elastic.
Yep. So if you think about a rubber band.
Yes.
So elastic deformation, and we're going to use green here. Elastic deformation is where, let's see. So we've got the area before, it's kind of this like linear area right at the beginning. It's the area before it, I forgot a word, and then I'm going to say the word and I'm going to tell it to you immediately. It's the area right before it yields. So yield is this point on top. Oops. And it is the end of the elastic region. In polymers, we typically put the yield at the peak there. In metals, we actually calculate the yield differently. But the idea is still when this linear region here ends, we get our yield point.
With metals, it's the 2% thing or whatever.
Exactly, yep. So with
Over.
metals, we calculate this line here. We increase this line by 2%, and we draw like a second modulus line. Oh, and I just gave you another one. So you get this second line here, and we would say the yield is like at this point for a metal. It'd be
Okay.
like right here-ish. So yeah,
Gotcha.
we do calculate that a little bit differently for metals and ceramics, or metals and polymers. Again, mechanical testing is very specific to the material we're running. So.
Yeah.
Okay, I just like handed you one, and I labeled one of them as modulus.
Yes.
So that's fun. So modulus is the slope of the line. I'm gonna just draw a little like triangle there because that's how we indicate that we're measuring the slope. Often you'll hear like Young's modulus or modulus of elasticity. or elastic modulus, which is just another way of saying modulus of elasticity. And those are different equations that we can use to figure out what that slope is. Again, different material applications as well. Okay, awesome. We're moving right along here. Since we have elastic deformation, do you know where plastic deformation is?
The second half.
It is the last, everything after the yield. Okay, where's the break on this?
The X at the end.
It's the X at the end, really subtle there. And is there a color I haven't used? I haven't used red. And the energy, and that's the total amount of like effort that my superhuman would have to put into breaking this, is the area under the curve.
Gotcha.
Yeah, okay. Some additional language as sort of a subset of number 5 here. You'll hear, sorry about that. You'll hear the word ductility. And it's the full range. So it's everything along the x-axis there. Area under the curve, same thing I've labeled as energy.
Right.
But you will also hear the word toughness. And that is the area under the curve after the yield. And less frequently, but still sometimes, you'll hear resilience. And that is before the yield. So all of those are sort of a subset of the area under the curve. And you'll hear ductility and toughness sometimes, especially out in the world. Resilience we talk about with people, but not with materials nearly as much. Also toughness, I suppose, for people. Thing we hear sometimes. So just, you know, if you're calling someone resilient, make sure you know that they're in their elastic period,
Okay.
not their plastic period.
Good to know. Good to know.
So now we're going to talk about what causes breaks and failures in the material. So our goal here, bless you. There's the quietest sneeze. Our goal here is probably to break the material. It's to test the mechanical properties. Sometimes we only test in the elastic region. So sometimes we don't, you know, we don't actually want it to fail. But a lot of times we are studying the failure of a material. And there's a couple different things that can cause or resist breaks and failures in the material. On the macroscopic scale, so this is stuff that we can see and stuff we can interact with. We're going to start over here. Let's say we've got a perfectly nice, clean, homogeneous sample. I am, let's say, a polymer maker, and I made this sheet of plastic parts. And I've got this really nice, very clean one. There's nothing inside of it. There's nowhere clear to start a crack, and there's nowhere obvious for the crack to propagate. So this is going to be a stronger piece because I can't start and I can't move a crack across. When the crack starts and when it does finally propagate, it's going to be random, and that means we're going to have it's going to take more effort for the crack to go through. So this is going to be a stronger material. Now let's say I have my perfectly homogeneous material, but while I'm cutting it out, the scissors snip a little crack in the surface. And now I've got this deformity on the surface. As I apply, oops, sorry, my eraser's all over the place right now. Boop, boop. As I apply force to this sample, the right side of my sample is going to deform a lot more than the left side because these are no longer attached, these two edges together. And so I have somewhere now where the crack can start, and it's very like, yes, the crack wants to start here. And because my little notch has a direction, there is a very clear path for the propagation of that crack as well. This is going to have a lot lower strength, a lot lower total stress than my nice, clean, homogeneous sample on the right-hand side here. Because we can start and propagate the crack very easily. There's not as much randomness to it. So these kind of surface defects, and those defects can be anything from like scratches, it could be like contamination. So it could be like I have a chunk of, I don't know, sand that landed on the surface of my material and it's making it weaker. That could be bubbles. That could be clumping if I'm working with like a ceramic powder and I end up with a clump of material on the outside or a rock. So all of those have the ability to start and propagate a crack really easily if they're on the surface of the sample.
Does it matter if the crack was at the middle or anywhere else?
Do you mean middle like vertically, like up and down, or middle left and right?
Like up and down.
Up and down. No, it is more likely to break the closer to the middle it is. But my crack could, or my notch, I guess is what I'm calling it. My notch could be way up here, or it could be way down here. But it's creating a much smaller.
That will be easier to crack.
It's gonna crack at this notch.
But if the notch was on top, would it be harder to crack?
Nope. We have the same principle where we are pulling more on the edges where it's detached. And that crack is going to propagate through from the notch if it's up here or if it's down here.
So it doesn't help if it was at the middle?
Nope.
Okay.
No matter where that notch is, if you've got an external defect, is what this is called, it's going to cause some problems. And then we have sort of this middle ground, and I'm gonna try to erase, well, I'm gonna try to erase some of these. So let's say I've got whatever thing, you know, scratch, bubble, whatever. It's probably not a scratch. But now let's say this is in the bulk, in the center of my material. It is not exposed to the outside. This is an internal problem, an internal inclusion. So this would be more like a bubble in my polymer. The crack may start here on the edges of this bubble, but more likely the crack is going to have to start along the edge somewhere. Edges tend to be where cracks start, although they can start from the center sometimes. Which means that we don't have a clear path for where this crack is going to start. But once it does start, if it happens to intersect with this bubble, so let's say my crack meets the corner of the bubble, it now creates an external defect, in quotes. by the crack reaching the bubble. And then I have a very clear propagation path where it's just gonna crack through the bubble out to the other side. I don't know why sometimes it does that really thick. Sometimes it's really thin. So I have an easier propagation path, but I don't have as easy a start. So this is kind of gonna be in the middle of these two. If we've got very strong, very weak, and this is gonna be somewhere kind of in the middle. And the problem with this is if I am the manufacturer and I only brought these 3 samples to be tested, I'm gonna have a huge variance from sample to sample. I'm not gonna get any information about my actual material from these 3, because I'm gonna average really good, really bad, and kind of eh. And I'm gonna think that all of my samples are kind of eh, because it's kind of halfway between good and bad.
Yeah.
When maybe this was just a one-off. Maybe this was a one-off. Maybe this is my standard. Or maybe this is my standard. But I can't know with just these 3 specimens. I can't know what applies to all the rest of my specimens back at home.
So how many do you need to test?
So typically we'd have a minimum of 5, sometimes as many as like 50 or 100 individual specimens. The best way to handle this though is like, don't allow bubbles and don't allow scratches. Do your best to ensure the integrity of the material from a mechanical, like macroscopic standpoint, so that you have as many of these as possible. That's kind of the goal. Beyond that, random sampling is kind of our best bet also. Zooming, there we go. So those are some macroscopic reasons why we might get failure. Scratches, contamination, bubbles, clumping. Those are typically within the control of the researcher or the manufacturer, and those should be controlled for. If you want consistent mechanical results, you want to have consistent manufacturing of the material. Now, on the molecular side, molecules and atoms will arrange themselves differently depending on the material. So polymers are going to be more amorphous. And amorphous means randomized. Oh my gosh, wow. Apparently I've forgotten English entirely. Polymers are going to be like these long, loopy molecules, and they're all just gonna like, you know, sit on top of each other. And a lot of times they also have these cross links, so they're like, this molecule is attached to that one, and this one's attached to that one. And you end up with this like pretty nice structure, because as I pull on this, we're probably just going to stretch these molecules. So if I were to grab this and I were to pull, I can just stretch exactly the way it is being portrayed here. Like these molecules are just gonna like spread out a little bit, but that's not like this huge deal for them. Eventually, cross links might start to break. Let me see if I can selectively erase a cross link or two. Oops. Probably not, honestly. Let's get in here with my detail eraser. So maybe eventually I'm gonna get these breaking of cross links, and then the material is going to stretch even more. So that might be the yield that I see. When I come up here, maybe, I hate when it jumps like that. Maybe this yield is because I started to see some cross-linking breaking, but I still have a lot of stretch that I can do because I'm not breaking the molecules. It takes a lot of effort to break a polymer molecule. When they do finally break, it is because they are stretched out to their absolute maximum. I needed to stop jumping! And it's because I have like aligned all my molecules.
So So when you break
And then eventually,
polymer by mistake, you just broke the cross-linkers.
no, if the polymer breaks all the way through, it's
No,
because,
like if you just in half.
yeah, if a polymer breaks, we are breaking the molecules apart from one another. The breaking of crosslink would be a yield. So
Wouldn't break.
it's not a break, it is a yield, which means that the material is now deformed. So plastic wrap, you can do this. You can stick your thumb into it. You're not breaking it, but when you pull your thumb out, it stays stretched out. You can sort of see the imprint of your thumb. So that would be this middle stage here, where I've like maybe broken some of the crosslinks. And then finally, to actually tear it apart, I've actually drawn this sort of poorly here. Oops. I want the stroke eraser. There we go. The break is probably, or the crack is probably going to go between molecules. So you'll have kind of this jagged edge. This is made more obvious. This is exacerbated or like enhanced if I happened to have any particles inside. I'll just take this whole thing. So if I have like a polymer with chunks of, I don't know, let's say like carbon inside, and we'll use a brighter green for my little chunks of material. So they're, wrapped up inside of this, and maybe they're like kind of weird shaped, or they're kind of longer, or maybe they're round, but those are going to continue to fill the space even after those cross links have broken.
Nothing happens to it?
What do you mean nothing happens?
Doesn't stretch?
No. The particles are surrounded by springs. Let's say you're sitting on a trampoline and someone starts pulling on the springs of the trampoline. You yourself are not going to stretch, right?
Yeah.
But the springs around you, this trampoline itself is going to stretch. You're just gonna kind of sit in the middle. And then these particles, even after we've stretched the polymers all the way out, the particles are still kind of in the way. So my crack might be even more jagged because it has to make its way around all of these particles. On the flip side, maybe the particles create damage to the polymers. So like if the particle like breaks the polymer right here, maybe that simplifies breakage. So we could kind of have either a strengthening, or a weakening effect from those particles being in there. And that tells us information more about how the particles and the polymer behave with each other. It doesn't really tell us much about like the polymer on its own or the particles. It's more gonna be like, hey, you have so many particles in here that they are keeping your polymer molecules from sticking together. Or hey, you have so few in here that they're making no difference whatsoever. So it can change the strength of it. So that's amorphous materials there. Things like metals. Oops, I am on my light green, which is a little harder to read, my guy. There we go. Metals and ceramics are crystalline. crystalline means that they have some order to them. So metals will sometimes draw, if everything is nice and ordered, we can draw this shape where they're like all lined up in a row here. If I cold work the material, meaning I take my paper clip and I bend it back and forth, then I create breaks through the structure, and it ends up looking a little bit more like this. Where the whole top of my structure has sort of shifted with relation to the bottom of my structure. When a crack is traveling through here, having perfect, reliable kind of highways for the crack to travel along can make the material a little bit more can make it easier for like sliding.
What do you mean sliding?
In this perfect crystalline, if I were to push on it, these two sections can kind of slide past each other. And I'm going to get this kind of softer, more malleable behavior from the material. With this second example on the right-hand side, that can't happen. I can't just move these three because they're attached then to these four, and this line kind of keeps them from sliding past each other. So on this one, sorry, I'll write out what I'm saying. Softer, more ductile, because things can move past each other. This one on the right is going to be harder and less ductile. Did we talk about ductility up a little higher? Yes. Ductility being the area under the curve. Coming back here, we talked about ductility here. So that's going to change how these break, how much stretch they can give. This one is going to have more strain, and this one is going to have less strain before they break. And ductility also has to do with strength, and these can affect the strength as well. So those are just some examples of like a microscopic or molecular scale property that can change the outcome of why something might break. In this case, a crack might propagate through, and it's going to have to break this barrier in order to propagate through. So it's going to take a little more effort to break through there. But it's also not going to slide quite as much. So. Okay. Any questions about what causes breaks? Cool. Typically it's bond breakage. Sometimes it's just because there's a path. Okay, let's talk about sample preparation. We talked about surface defects earlier. And what we really want is homogeneous samples. And when I'm talking homogeneous, I'm talking mechanically. I'm talking like physically. So their physical form should be homogeneous. I am talking chemically. I'm talking surface finish. As homogeneous across the whole material as possible. When we are doing tensile tests, well, let me draw the what doesn't work first. let's say I've got a rectangular something or other, and I want to test that in tension. So that's pulling. I have to grab onto this material. And if I don't want my fingers to slip, and in this case we're talking about like the grip of a testing instrument, I'm gonna have to grab onto it maybe with like my fingernails. So I've got this like bumpy grip. It's gonna grab here and is gonna grab here. If I had a perfectly homogeneous, smooth surface, and then I used my fingernails to grip into it, where is the weakest part on that sample?
The place where you grip it.
The place where I grip it, yep. So this becomes the weakest point. It's going to break where I grabbed it. Coming all the way back up here. Ooh, that was a lot of scrolling. If I have gripped this and I've caused an indent, this is now my cross-sectional area, right? So if I gripped it and I made an indent here, my cross-sectional area is no longer square, it's now this funky shape.
Yeah.
I can't calculate that. I don't know exactly what it is. We're on the order of probably microns now, which means that I am not properly calculating my stress values. So failure at grip, which is what will happen here. And that is considered an invalid test.
So what do you do?
So we shape them and we call what we do, or we do what we call a dog bone.
Oh yeah.
And it's a sample shaped like this. Now what I'm gonna do is I'm gonna use those same grippies. But even if I indent with the grippies on those wider areas of the sample, the weakest point is actually right here in the center. And I can calculate the cross-sectional area properly for that section. So this one I'm going to have failure in center, valid test. The struggle a little bit that we have with this one is that the length, remember we care about, length in addition to our cross-sectional area. The length that is actually extending is this, because it's everything in between the grips is extending. But the length of the area that I care about is actually this smaller region here. Oops, I have a grid. Follow a straight line, my guy. So it is recommended to use an extensometer.
Guess what?
Sorry, I'm right-handed and blocking your view there. Use an extensometer, which instead of measuring the length of the whole thing that's extending, it's going to measure the displacement just over a small area. Out. Nice, not too close to the edge. So it's going to measure the displacement only over that L0 section, not over the whole, grip to grip area. So we've made it better and then also made it more complicated by using a dog bone shape.
Sure. But does it work like
Yes.
perfectly?
Yes.
Almost?
Yes, it is. That is the accepted method of testing dog bones. You can use an extensometer that clips on, and it just like grabs onto the sample and it measures how far the sample stretches in those two places. Or you can get a video extensometer, which basically tracks the points of pixels over the course of the test, and it'll measure how much different areas extend over the course of the test. I think those are really cool. It's a nice tool that people have invented.
Okay.
For compression samples, if I have any sort of like jaggedness on the top surface or bottom surface, I want to cut the sample so that it is perfectly parallel. Why? Because if I had a flat plate that was coming down and it impacted these 2 points first, it's going to look like it's starting to crush the sample when really it's just collapsing those bumpy pieces. Does that make sense? And my cross-sectional area, again, like I can't calculate the cross-sectional area of those 2 points. I don't even know where it's hitting. So I want to make sure that when I'm making contact, that I'm making contact here at the nice flat surface. I also want to make sure that I have a consistent cross-sectional area. So that would mean like shapes like a cone, even if I chop off the top and the bottom, not ideal. Because I don't have a consistent cross-sectional area. That's going to be really complicated to measure my force and displacement, or my stress and my strain. Some people don't care. They just want force and displacement. And that's just fine. You can do a weird shaped sample if you want force and displacement. But if I want to get stress and strain out of it, I have to have a good uniform cross-sectional area, nice flat top, nice flat bottom. Okay, any questions on that?
No.
Okay, we're gonna do one last little section here. We are going to talk about statistics.
Can your sample be circle?
Can it be a circle? Do we have an even cross-sectional area if it is? Are you talking circle laid flat on the plate, or are you talking about sphere? Like a disc or a sphere?
A disc.
Discs are just fine because they have this uniform cross-sectional area. I would just lay it, so if this is my plate here, I would lay it on my plate flat.
Okay.
I would not want to do it standing up. So I wouldn't want to do it like
sphere.
this, or like a sphere. Yep, because I have a changing cross-sectional area. And in this cross-sectional area we're talking about is this. That would be my cross-sectional area there. Look at me throwing drawing in 3D. At least in our department, statistics is not required. I kind of wish it was, because material scientists work with so much data. It's important to understand what is significant and what is not significant. So really, like, broadly, don't show a statistics professor my explanation of statistics. Let's say I have those 3 samples from above, and I test them and I get one really strong and one like not so strong and one kind of in the middle. In this one, I'm going to say that this is my average.
What is the axis?
Sorry, this is, I've got maybe max strength.
Oh.
And then this is just like group number. This is like my first group, I only have 3 specimens. And one of them is really strong, one of them's not really strong, and one's right in the middle. If I were to take the average of all of that data, it would be right there in the center. But I have a really high standard deviation, right? So I have a lot of variability in my data. Now let's say instead I test 5 specimens, and I find that this is more like my distribution here. So I'm getting more specimens that were strong. Still some that were really weak. Still some that were kind of like a little bit weak. But I'm getting more of these strong specimens. In this case, my average is here. And I have like an standard deviation. Good. And then let's say I run a test. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. It won't be. 37, 38, 39, 40. So now it's quite a bit clearer to see. That is not even vaguely what I drew. Can you tell visually where my average is?
Yeah.
Yeah, right there. I'm actually curious. Can your pen write on my iPad?
Mm-hmm.
No, not paired. Makes sense. So now we can see that my average is here. I still have a standard deviation, but I'm going to have a much lower standard deviation because I have so many points right around my average. It's fine. You don't have to draw 40 points, but the idea is you can see very clearly I've got these clusters of like probably some of my specimens had scratches on them. And I can see a little cluster down here. And I've got also a little cluster here, and that cluster lines up with the average of the orange group. So those were probably the internal problem, specimens. So I have a couple of those. But on average, most of my specimens are not, don't have any, issues. Really generally, the more data you collect of the exact same thing over and over and over, the more you can trust it. So this orange one, I can't trust this value. It has a really high standard deviation. The blue one, I can trust a little better because you see it's getting a little closer to the true values. But one random, like if on this blue one, if I had gotten, bless you, one random like hit way up here, that would have thrown my average way up higher.
Yeah.
For one data point. Ideally, if I collect one specimen, I should not vary my average that much, even if it's an outlier. It should not drag my average way higher or way lower to just get one outlier. So for this reason, I want to collect groupings. So I'm gonna bring a whole slew of specimens to the lab. I call this a sample. Multiple identical things. And by identical, I mean they were made in the same batch, they were processed the same way, everything should be the exact same. One of them we call a specimen. And a specimen is one thing to break. We're gonna get one data point out of this thing.
That's it?
In a lot of other characterization techniques, we use sample and specimen interchangeably. So we were like, give me the sample. And when we're talking about the sample, we're talking about one individual thing. But with mechanical testing, statistics is insanely important. And so we will talk about one specimen, and a group of specimens is a sample. With my last few moments here, we're going to talk just a little bit about time, which we already talked about a little bit. So time and other variables. So we mostly were talking about force and displacement being our two variables, but we can have temperature being a variable. We can have time, obviously, I literally just said that. We could have atmospheric. We could have atmospheric conditions, is what I was gonna write. That would be like O2 versus like CO2. Like, how does a different gas surrounding the material? But you're right, we also can have atmospheric pressure. So that would be different than the pressure we're providing to the sample. But that could be like, I will do that as like a sub point here. And from other variables, and a caveat that should already sort of be built into your scientific understanding. When I'm bringing in another variable, everything else should not be a variable. So we should be holding force and displacement still generally. So if I'm like changing temperature, maybe I'm measuring force, but I should hold displacement still. Or if I'm looking at time and I want to keep the displacement still and I'm measuring force. So not a ton of variables all at the same time, because that confounds things. But we can get information like creep, relaxation, aging.
What do you mean relaxation?
Relaxation. If I took a piece of plastic wrap and I pulled on it a little bit, not enough to like really, really damage it, but I pulled on it a little, and I just stood there for a long time, eventually the plastic would stop resisting my pulling. It would relax. Other things that'll do that would be like a memory foam. So if you like push down on it and then you just like hold that pressure, it'll start to lower. It'll start to kind of like relax even more under that seam pressure. So relaxation is where force or displacement change in order to relieve the force being put on. I guess displacement changes in order to relieve the force being put on the material. That make sense? It can also be a molecular relaxation. So we talked about polymers up here. This would be an example of relaxation as well, where the material is able to stretch from this point to that point. And it's just like the polymer chains stretching. And they kind of stop fighting eventually. They're like, oh, well, now we're stretched out, I guess. Aging would be how things are going to change again with time, but aging can also happen. It could be a temperature-related thing.
How do you test aging?
How do you test aging? Depends on the kind of aging that's happening. Sometimes you can see visibly that like material is flaking off or it's starting to wear out.
If you want to test it and see how long it's gonna last, but like you just have a new sample, can you do that?
Yes, there are labs that do, it's like weathering testing or aging testing, and they usually use a combination of UV light and heat and humidity, and they cycle it really rapidly. So they go like hot, cold, hot, cold, hot, cold, hot, cold, or they put it out in really intense sunlight and then dark, and then intense sunlight and dark. They do that for a long time as well. Takes a long time to measure aging, but there are ways that we can speed up the process to get an idea of how this thing is going to react to aging. Yeah.
Okay.
And some of it is just time related, and we can't predict necessarily beforehand with preciseness. But there, we've had enough materials around for a long enough period of time that we can take some context clues. We're like, hey, that billboard is failing early. Whatever material they used was not great, so we're going to use a different material. A little bit of in time and a little bit of accelerated.
Okay.
So all of these can be applied to all the stuff I was talking about earlier with mechanical testing. I can add temperature, time, and different environmental conditions to change how these results are happening. They're not as common to change these, but doable.